these past couple of months have really also put a lot of food for thought and for reflection for a lot of us. So I hope you all are staying safe and healthy with you and your family. And that also motivated a bit of what I decided to talk about today. So instead of exactly following the abstract of my talk announcement, I decided to make some last moment changes. And that's really motivated by this ongoing crisis that we're living through. So I would argue that the thesis of my talk is to suggest that, as the power grid, as a prime example of the energy infrastructure, we really have to think about how to advance and enhance the resiliency of such infrastructure through digitization, and more particularly through some domain-tailored AI. And I'll try to elaborate that in a couple of examples. So this is really joint work with a lot of dedicated students, postdocs, and collaborators. So I wish to thank all of them. As everybody was thinking about, what's going on in this COVID, right? And electricity is the lifeblood of human society. So how is electricity infrastructure doing? So I would like to give you some really up-to-date information about that. And then I would like to perhaps move on to argue about what digitization means for critical infrastructure such as the power grid. What it means what are the research challenges and opportunities? And then I'll be examining some possibilities through a couple of specific examples that we have worked upon. And I'll be ending with a sort of some of our thoughts at the Energy Institute on what can we do collectively to advance this ongoing revolution of energy digitization. So this is something fresh off of the press. This is I guess the title have suggested. This is the New York City. If you are familiar with New York City, you can see that is the Manhattan down on the, and then the Atlantic Ocean. And this is what we are showing you here is what NASA captures using the satellite image before the lockdown order and during the lockdown order. What you see on the left is at midnight on March the 8th, 2020. What you see on the right is midnight of April 25th, 2020. What you see on the number on the top is the average intensity of this figure. Namely, you can roughly thought about this as a brightness of the city. So what can you see? I was really shocked when we look at this data. COVID has lowered down the city brightness by as much as almost 40%, right? And we all know the city light is a vibrant sign of human activities. So we are going through this crisis as we speak. What about nearby? This is Houston. What we are capturing here is by the way, all this is post-process data. Namely, we already eliminated the ambient lighting situation. So what you see here is really a reflection of the human lighting conditions. This is the midnight of February 28th of Houston. As we all know, Houston is a much more spread out region than New York City. But still, you can observe some considerable amount of drop in the brightness of the city lights. So what can we see? We are literally going through a once-in-a-generation crisis, and we are still going through that. So with that in mind, we have been thinking a lot about what can we do as a community to really contribute something to this solving this societal challenge. And one thing I'm happy to report is that thanks to the hard work of many postdocs and students in our group, we are pleased to actually launch today, as we speak today, the first of its kind, to our best knowledge, the first of its kind, cross-domain a data hub for analyzing the impact of COVID-19 on the electricity sector. It combines electricity market, it combines public health data, it also combines other data sets such as satellite imaging, such cellular data, such weather data, and we call it CDEMDA. I'm sorry for the acronym. We're not very good at that, but this is what you get. And it's already just published today. So you can actually go and check it out. It's available now on the GitHub. And you're more than welcome to use this to facilitate whatever interest you might have for data-driven analysis, for data-driven assessment, and data-driven prediction of what's going to happen on the electricity sector. And this is also a working paper that we just uploaded fresh 30 minutes ago. We just uploaded to the archive, and you're more than welcome to take a look. So this is how much about how the electricity sector is handling, as we speak, this short-run impact from the COVID. But if you take a slightly longer perspective, how is this electricity sector going, in terms of the long run? I think this is sort of what we are thinking about. I think the power grid, during and post-COVID is going to accelerate three key trends. The first one is going to continue acceleration of decarbonization. By that, I mean the integration of massive amount of renewable and low carbon resources. Texas, for example, is already taking more than 25% of its electricity coming from the wind energy. And the second one is electrification. That is to say, a lot of other means of energy demand that traditionally would have not been used through the means of electricity will be electrified. The prime examples include electric vehicles and industrial heating and cooling loads. And really, I think what is at hand is on the bottom right corner, and that is a general term I would call digitization. By that, I mean the proliferation of sensory data, communication capabilities, and computing capabilities. And all of that are really trying to suggest that we can envision a whole different kinds of energy infrastructure that is going to have a prime example in the context of electricity. And digitization offers this very unique opportunity to advance this resiliency of the grid. As I was talking to one of the a very senior person in Citibank. He used to be the chief risk officer of Citibank. And he was saying like how COVID is affecting the industry. A lot of companies might not want to spend that much resources on real estate because people can work from home. But then the flip side is the society will have to spend more money on the infrastructure to support such a new paradigm, right? And the example and a key enabling infrastructure would be the advancing the resiliency of the grid. So the thesis of this talk is really, how do we leverage all these available data and computing and sensing capabilities and to advance the resiliency of the grid through what I call domain-tailored digitization. Why domain-tailored? Well, I think machine learning and data science in general has achieved tremendous amount of success over the past few years. And I don't have to motivate too much about that for the audience like you. So the question is, what should the infrastructure system like the power grid do? Should we simply just take whatever example and success from the AI or machine learning and then just plug into the particular problem? Or there's some subtle point that we need to think about. And my argument is that there might be some subtle points. And those subtle points might well be also the opportunity for researchers to make a difference. So what are the subtle points? I would argue that by and large, in machine learning or AI as of today, most of the industrial success are in a lot of the so-called static application areas. Think about things like computer vision, your Siris, Amazon e-commerce. All these are by and large static problems. The concept of time is typically missing. Whereas if you think about, industrial infrastructure systems, a lot of times that requires the notion of time, and more particularly, what I meant is that it requires some notion of the underlying physical dynamics, and that perhaps is a key feature and desirable, a research opportunity for making progress of AI for safety critical infrastructure systems. So I would argue that perhaps there are three features if AI were to make successful implication and impact on such infrastructure systems. The first one is that these new kinds of AI will have to be respecting the safety criticalities, right? You take a selfie out of your iPhone. If you don't like it, you just redo it. You don't restart the power grid that easily, because restart the power grid means major blackout and major cost of life and dollars. If you Google search somebody's name, and if that link pops up 1 second later, you're a little bit upset, but that's not the end of the world. But if you are developing an AI algorithm for controlling the grid, and if that control algorithm does not come on time, the system is going to undergoing some major collapse. So AI for such safety application will have to respect time sensitivities. If you talk to a power system operator and then tell him or her that this is an AI algorithm to support the renewable integration, so that you should shut down that particular power plant in West Texas, they would say, go away in a nice way. But the reason is that if you cannot explain why you come up with this decision, chances of success are likely to be reduced. So one has to develop not only successful examples of AI application, one also have to think about how to explain those results to the actual system operators, infrastructure operators. And as it is the third desirable feature, and that is physical interpretability. So this is really what I think has been driving a lot of the research agenda in our group. And that is to say, how do we take those streaming data and how do we make near real-time decision-making with the above three desirable features, such that we can know what is happening, where is it happening, and what could be done, right? And in the interest of time today, I'll be focusing primarily on this blue colored points. And I'll be showing you through some concrete examples. The first example is coming from the bulk transmission level high voltage power networks. And one of the biggest story in the past 15 years in the power grid is the proliferation of new sensors. And this kind of new sensor is called phasor measurement units. If you have never heard about PMUs, phasor measurement units, think about it as a GPS synchronized, high fidelity, high sampling rate electrical sensors, right? So what's the state of the art before this? The state of the art before this is something called SCADA, supervisory control and data acquisition, which samples the grid on about every 2 seconds, and PMU advanced that by 100 times, right? So because it's synchronized and sampling at a 60 hertz typically. Not only it is 2 orders of magnitude faster, it is more importantly synchronized. That is to say, if you take a measurement from the East Coast and you take another measurement from the Midwest, you know exactly the time because of the GPS. And that time turns out extremely important to align the measurements together, because this is an underlying dynamically evolving system. So 15 years ago, there was probably a handful of this. Now I think we have more than 2,500 in North America. So these are streaming, high quality, fast data to the control centers in a continuous basis. So what can we see, or what can we, what is different that this sensor makes? Well, you can now begin to see what's going on in the grid in a dynamical sense, right? So this is actually some real measurements for the Eastern interconnection. Well, if nothing else, it is cool to see that, right? Before you could not even see that because the sensor were too slow. What else? Well, you can see that the grid was never at a steady state. The grid is always changing. And it's almost like a human being breathing in and out, right? In and out, in and out. It's cool. So, if you ask a kind of a Congress type of question, what's the value proposition of this investment? Well, one thing is that you can improve significantly the visualization of what's going on the grid. But, if you ask a very experienced power engineer, you say, okay, what's going on this? He or she might be saying that, well, it looks like there's some kind of a small, oscillation going on, but not a big deal, because if you look at the the frequency measurement, that is the floating bar, the frequency was actually under very tight band. It's like something between 60.015 and 60.025. So all is good. It's just a small perturbation. You're turning on your light, you're turning off your light, things of that nature. It's not a big deal. So they may say, well, okay, it's good that I can see what's going on, but you know what's next? Well, this is some more serious problems, and this is also something happen in the real world. So it turns out that if you have more and more renewables, you might have some of these interesting problems happening on the grid. So what's the problem? Let me just explain this in 1 minute. Now we go to the West Coast. There is a power plant in Alberta, Canada. And this power plant is a power plant that suddenly had a 20 megawatt oscillations. 20 megawatt peak-to-peak oscillation in power system language is not a, I mean, it's okay. It's not a big deal. It's 20 megawatts. But what is very strange is that some 1,000 miles south between California and Oregon intertie, people observed 200 megawatt, that is to say 10 times magnified oscillation at the same time. And that came out of nowhere. And at that moment, the system operator in California had no clue what was going on. And then that caused a brief moment of system islanding and blackout. So I don't know about you, but if I'm for me as a power engineer, I really got excited by this kind of problem because I want to solve it. It would it be nice, because now that we have all these fast sensors, these PMU measurements, would it be nice if we can actually know what's going on, that there is this California, Oregon intertime 10 times magnified oscillation? And would it be nice if we can locate the problem, the troublemakers, this power plant in Alberta? And would it be nice if we can do some decisions on the fly instead of waiting to the end and then do some post-event analysis and then figure out, oh, this is what happened, right? So we want to solve this. But it turns out it's actually not that easy to solve it. Why? I will talk to you I'll talk to you about that in just a minute. But one thing that it turns out it's very nice about this PMU data is that even though they come in with a lot of amount and with high dimensions, they are showing some incredibly low underlying dimensionalities. And we collect this data from all three US North America interconnections, West grid, Eastern grid, and Texas grid. They are all suggesting the same kind of a behavior. That is to say, even though we have lots of these PMUs, but if you're actually making a look at this streaming data, all these streaming data are exhibiting at incredibly low dimensions. So that, I'm going to just have a hint here, because we're going to utilize that later on when we are solving this California problem. So let's talk about why is this locating such a magnified oscillation such an important and challenging problem. It turns out that it's actually not that trivial. So for the people who are not working on power systems, I would like to just give you a conceptual analogous example. Think about yourself throwing a stone into a calm pond, a peaceful pond. When you're throwing a stone into the pond, what happens? It starts some wrinkles, right? So where do you determine the source of the wrinkle or the source of this perturbation? Well, if you have all the measurements you need, I guess an easy way to tell where the source is simply to say, I want to see where the wrinkle is the biggest, right? Because typically that's where you throw the stone into water. When the stone hits the water, that's the place where you see the biggest wrinkle, right? Could we apply the same kind of a logic to the power grid oscillation? It turns out that it's not that trivial, and that is because what we observe in this real-world example in California, Oregon intertie is some category of the so-called forced oscillation. And forced oscillation is something that turned out to be very interesting, because there is essentially, conceptually speaking, excited by an external perturbation, in this case, this power plant from Alberta, and that generates some sort of oscillative behavior across the entire power grid, right? Tens of thousands of miles. Now the question is, how do you locate this source? If it were just a compound pond and you're throwing a stone, that's an easy problem. But in the context of power grid, things were not that trivial. Why? Because we found some very counterintuitive examples, namely the place that is close to the source are actually exhibiting a smaller amount of magnitude. And the place that is further away from the source is actually exhibiting some higher amount of oscillation. So that's counterintuitive, right? But it's actually not that bad because it actually has some intimate connection with what we all learn in the high schools. Everybody remember high school physics? We remember something called resonance? When there's an army of soldiers walking on a bridge, they're not supposed to walk in synchrony, right? Why? Because you don't want the soldiers to be walking in the same frequency of one of the natural modes of the bridge so that it may have generated some resonance of the bridge and then that may damage the bridge. It turns out that what we see in the real world in this California-Oregon intertie can be conceptually traced to the same cause. That is to say, there was a forced oscillation-led resonance of the grid. And when resonance happens, all bets are off. All this intuitive understanding are off. So we need to really think about how to solve this problem under resonance conditions by utilizing this PMU data, okay? That is to say, we would like to develop a method to locate such oscillation source even when resonance happens. So what can we do? We actually got stuck. We were making some nice progress on this low dimensionality, and then nothing happened. We got stuck for about 3-4 years. We made no progress. And then all of a sudden, we got some interesting inspiration from a seemingly totally different domain. That is from the domain of surveillance video cameras. I don't know how many of you have installed this surveillance video camera in your house, but that's basically a bunch of video capturing the images nearby your house, and they try to send you an alert if someone comes to your house, right? You may have received those messages or emails. So what's going on computationally speaking? What's going on computationally speaking is that the computer, these companies, these surveillance video camera companies, they're taking in your streaming video and they're trying to separate the so-called foreground and the background. What is the foreground? Sorry, what is the background? Background is this picture on the bottom in the middle. That is some unchanged scenery, right? What is the foreground? Foreground is basically a person, an intruder, is walking in the scene, right? So they try to separate these two because whenever they detect something on the foreground, that is on the bottom right figure, then they need to alert you by sending you a text message or email. Now, how do they do that? Did they hire people to actually just watch this video? No, they don't do that. They actually use computers to solve this for us. So what's going on in the computer? So what's going on in the computer is actually they're solving an interesting mathematical decomposition problem. So they're taking in all these pictures. These are the pixels of the camera pictures, and they're trying to separate them into the so-called background matrix and the foreground matrix. And whenever this foreground matrix is showing something non-zero, that's when they trigger this alert. That's when they send this alert to your cell phone or to your emails, right? So, how do we summarize or how do we extract the key property of the so-called background and foreground? It turns out that this background, roughly speaking, is talking about something that don't change much over time, right? So mathematically speaking, the property of matrix Z is what? That means the matrix Z is low rank, right? Because low rank means that your previous snapshot and the next snapshot is highly correlated. Things don't change much. What's the property or the mathematical property of the matrix X, the foreground matrix? Well, the assumption is that at any given moment, there's unlikely 10,000 people intruding your house, right? Most likely it'll be just one person or two people walking around your house at any given moment. So the property of this matrix X, mathematically speaking, is that this matrix is sparse, right? So the computer's job is to separate a streaming matrix Y into a low rank matrix Z, summation with a sparse matrix X. And that is called, actually, it can be summarized as a, it has some intimate connection with the problem of so-called compressed sensing, by the way. Yeah? So coming back to this PMU problem in the power grid, what we are hypothesizing is that perhaps one could think about this, across the grid oscillations, this reference mode as something that is of low rank, that's capturing the general trend of what's going on in the grid. And then there is this external source that is exhibiting this perturbation, and that one perhaps can be thought of as the foreground, right? That is the sparse matrix. So the computational goal is how do you compute such a matrix Z and X in an efficient, streaming, real-time fashion, right? So the original problem setup is on the left. It turns out that problem is kind of a non-convex and the NP hard. The good news is that over the past couple of decades, there have been tremendous computational strides on solving this problem by recasting it as a convexified formulation. Basically, you change the norm, right, into a nuclear norm. And that, it turns out, is very efficient to solve by methods such as augmented Lagrange multipliers. And then one can then designate this sparse matrix, the largest element in the sparse matrix, as the candidate of the forced oscillation location, right? So we tested it out using both a synthetic and a real-world examples. This is what a synthetic example looks like. It turns out that this is the bus 40 is the most severe oscillation, whereas the troublemaker, the problem that is caused by this malfunctioning of generator at G13, which is completely far, on the opposite end of the system, right? So these are very counterintuitive problems. If you're just looking at the PMU measurement, you would have been totally misguided. Whereas our method turns out to be almost 100%, not exactly, but almost 100% accurate. There's only one case that was wrong. And even for the seemingly wrong case, the result is not that bad, because what we suggest is the algorithm suggests it should be in generator 12, but the true source is generator 13. So they're actually electrically very next to each other. So that's even the seemingly wrong result gave us a very promising, hope in narrowing down the search space. So that's in a 68 node system. We then further studied this with Texas Grid, right? So we work with ERCOT. ERCOT is the Texas Power Grid Operator, Electric Reliability Council of Texas. So they were kind enough to actually give us all this real world data of PMUs. And they told us, yes, we have been bothered by these forced oscillations in ERCOT operations. Can you kind of help us? And then we said, okay, let's try. And then we were pleased to report that we found exactly the source, being the fastest one of something, right? So, so that's the kind of the good news of this effort. But then when we present this to the ERCOT friends, they say, all right, looks like the algorithm is doing its job and we're happy, but I'm still a little bit suspicious, because if you stop and think about it, so far we have just using only the PMU data, right? We have not utilized the underlying power system model at all, at least for up to now. So the question is, how do you explain why does this algorithm and this seemingly kind of a naive way of thinking, why does it work? Could you give us some physical interpretabilities, right? So I was, visiting MIT during my sabbatical, and I got a conversation with Professor Sanjoy Mitter, and he recommended an old book to me. Some of you may have read this Robert Wiener's book on cybernetics. It was published in 1960s. And there was one chapter actually devoted to the notion of forced oscillation. It turns out very interesting. But Wiener was coming more from a physics point of view, saying what's the mechanism behind this resonance. And but it turns out there's some interesting connection with the computational viewpoint. And that is to say, what we are suggesting is that we found that for any, it doesn't have to be power grid, for any linear time invariant dynamical systems, if you actually write down this time domain expression of the measurement matrix, y of t, and then you just break it down into different segments of this resonance and resonance-free component, the resonance component, can be proven to be exactly rank 2. Right? You can have zillions of measurements. It doesn't matter how many measurements you have, but if you write down the corresponding resonance component of all these measurements, you can have a precisely rank 2 matrix. So that we found was very interesting. It kind of also complements what Wiener was saying earlier, because he was coming more from a physics point of view, and this is coming more from a kind of a high dimensional viewpoint, a more kind of a modern viewpoint. So that's probably one of the possible interpretations. That is to say, the reason that this algorithm works so well is because this resonance component, and remember, this resonance component was the troublemaker for us, right? Those are the ones that, blew all the intuitive bets off, right? Because these are the ones that triggers orders of a magnitude higher magnitude when the resonance was triggered, right? So that was the physical interpretation, is that for this purely data-driven method, this low rank seems to be capturing this resonance component quite well. And what is left over is more in the sparse matrix. And that sparse matrix is resonance-free, and they follow the localized behavior. So to summarize, we kind of are suggesting an example of how do you utilize high-dimensional streaming data to localize this large-scale power grid force oscillation problems. The algorithm is totally data-driven, but the good news is that this data-driven method seems to have some nice physical interpretation. That sort of stylized a lot of our research in moving along this direction. Now let's kind of move on to the, another very important aspect of what's going on in the grid, and that is kind of a one step closer to our household. That is on the distribution grid. For those who are not in the power engineering domain, the way we differentiate high voltage bulk power grid and kind of a retail level systems is what we call transmission versus distribution. Distribution grid is anything below sort of a 69 kV, right? So this is basically your neighborhoods, cities of college-station, sorts of things of that nature. Right? A lot of things are happening on distribution grids. One of the common, often mentioned example is this so-called duck curves, right? So what is duck curve? Duck curve refers to those increasing level of distributed energy resources, such as solar panels in your household. And because of those deep penetration of solar panels, it makes the net load behave more and more like a duck, right? A duck looks like what you see here. That is to say, your peak consumption actually will no longer be on the daytime, but rather it will be closer to the kind of a sunset time, right? When everybody goes home to start, at home, working on cooking, and when all the sun is set. So a lot of things are happening on distribution grid, and one of the biggest, I guess, perhaps unsolved challenges is how to maintain the physical and cyber security, right? By physical security, I mean that you have to make sure that the protective relay and the whole protective devices work properly when there are some major, events happening, right? So that's the so-called physical security. So I'm going to address that problem in the next 10 minutes or so, and I'll wrap it up. So what is the architecture of today's distribution grid, right? I'm pleased to see some of the friends from Sandpoint is calling in today, and so they are at the front line of this. So in a nutshell, distribution grid, it's really based upon, this traditionally hierarchical structures. That is to say, a utility company would give action control orders to the substation. The substation will then pretty much automate most of their, of their control actions. And among all of this, one of the key pieces is the so-called protection, right? So what is protection? If you have never heard about protection, look at your panel in your house, or think about in the old days, a fuse, right? When there is a fault happens, your protection is supposed to trigger, right? In other words, you want to separate normal situations from abnormal situations. And protection devices are very expensive. We're talking about 100 billion kind of asset industry, right? Today, it is by and large a offline, once for good kind of a relay setting. That is to say, utility companies will install these relays and protections throughout the distribution feeder lines all the way to your household, and they will just leave it pretty much unchanged, right? And our argument is that this is not going to be a suitable paradigm for the future, right? Because a lot of things are happening on the fly. So you have to make those protection devices much more robust and much more adaptive. So the question is how? So we found some inspiration actually from the field of machine learning, and then we're going to show you that. Before we show the opportunities, let me first show you some challenges. Why, having all these distributed solar and other energy resources will make today's protection not work so well? The reason is because the traditional relay setting, the protection relay setting, are by and large based upon the assumption that power goes one way. It's a one-way street, all the way from high voltage system to the substation, and then to the recloser, and one step further to your household. So power and current goes one direction, right? But with the proliferation of distributed energy resources such as solar, this assumption will be rendered invalid. So I'll give you this example that everybody with high school physics should be able to understand. So if you look at, there is a panel in the household, and there is a fuse in the house. If there's a fault that is happening, for example, if there is a line to ground fault in this place, what happened is that a fault basically means there is a voltage close to zero, right? It's close to the ground, that means close to zero. Then it's going to inject, trigger a large amount of current flowing from substation all the way to the end point, right? Because the substation is still behaving as a voltage source. That means there's a high voltage. And then because of the voltage difference, it's going to generate a large amount of current. But precisely because you have a solar panel next to the fuse, solar panel is what? It's basically also behaving like some kind of a energy source, right? So that means the solar panel also is going to have some level of voltage level. And because of that, we all know the basic Ohm's law. The point between the solar panel and the recloser, this period will not have that much of a current because the voltage difference is not that big, because the solar panel is kind of a boosting up a little bit at the point of interconnection of these local voltage levels. So the recloser, the red colored recloser, becomes confused because what he sees, what this recloser sees, is this I sub. And this I sub is not substantially higher than a normal situation. So then it gets confused. Is it a faulty situation? Or is it just a little bit of an increase of current, which happens all the time, right? So one needs to be better in tuning those points. This is another example. If you have a distribution circuit that are in parallel, circuit 1 and circuit 2, and if there is a fault that's happening on circuit breaker 1 area, then the voltage at the circuit breaker 2 is still fairly large because there is a solar panel on the end of the feeder line. That is going to inject back a major current back to the circuit breaker 2. So it's going this way, back to the circuit breaker 2, right? And that current might be substantially higher than the threshold of the recloser on the circuit breaker 2. In other words, some faulty situation in another location may have caused a recloser in circuit breaker 2 to malfunction. That should have not happened, right? So the question really becomes, these two examples motivates the research challenge. That is, how could we be, more intelligent in terms of setting those thresholds for when to trip off these reclosers and relays, right? So we find that there might be some opportunities coming from machine learning, because it turns out that this is a high dimension decision problem. You're not looking only at a snapshot of the current or the voltage, but rather you're looking at a whole segment of current and voltages. And that in itself is a high dimensional decision making problem. And some machine learning might offer some unique insight in making such decisions, given such a combinatorial number of possibilities in the real world, right? So our whole argument is that for such high dimensional measurement decision problems, manual decision might be hard, whereas machine learning might offer some unique opportunities. And I'm pleased to report that we actually have done some work on this. That is, instead of thinking about the problem of a relay decision as a simple threshold choice problem in the traditional sense, we suggest that each of this relay decision making could be thought of as a multi-agent reinforcement learning problem. If you have not heard about multi-agent reinforcement learning, this is kind of like the this is what Google, the AlphaGo and AlphaZero. This is what behind all these success stories in the Go competition, and this also is the success story behind all these robotics successes, such as this Boston Dynamics robots, right? So what happened is that we reformulate the problem of decision making for these relays as a multi-agent reinforced learning problem. Why? Because we realized that it actually has certain sort of memory in making such decisions. One should not only look at the current or the voltage at the present value, but one should also relating what is in the immediate past to make such a decision, because that may tell you some trend of what's going on, right? And also one should be smart about how to design the so-called reward functions. For those who are very well versed in the RL, reinforcement learning literature, how to determine the reward function is also a big trick. And what is actually something very interesting, and coming back to my title, why do I call domain-tailored AI? Something very interesting in this particular example is that it turns out that the reward of this relay depends on others. In other words, it's a multi-agent problem, but it is kind of a multi-agent in a single direction. And I'll explain why that means. It turns out that this is a so-called nested reinforcement learning problem. Why? What it's to say is that, in general, a multi-agent reinforcement learning problem is kind of a hopeless, right? It's NP hard. You can never find anything about global optimum. Just try your best and hope for the best. But we want to say something more than just that. So it turns out a domain's knowledge, again, comes into the picture and helps us in a major fashion. And that domain knowledge is that we found out that the reward function setting observes some single directional property. All right? What I mean is the following. The performance of how well the downstream relay performs is somehow not dependent upon how the upstream relays are performing. I'll give you an example. Look at relay 1. If the upstream relay 3, think about a relay is a switch, right? If relay 3 is open, that is to say, it is switched off, it means open circuit, it doesn't matter what to do because relay 1 is de-energized, there's no electricity. And if relay 3 is closed, namely it is energized, then relay 1 should as well just do what's best for relay 1. In other words, regardless of the state of relay 3, the reward function for relay 1 is a local function. The converse is not true. Namely, how well relay 3's decision is going to be awarded is actually depend upon how what is the state of the relay 1. Because if your downstream is still energized, you better be careful, right? You have a different kind of decision versus if your downstream relay 1 is de-energized, right? So that's a tremendous computational saving for us because it turns out that it gives us a sequential training as opposed to a simultaneous multi-agent training, right? And then we can actually do this order of training using a depth-first tree traversal. And the policy of that, of the downstream relay will first be trained and set, and then you move on to the upper level of relays. And that's how it goes, animationally speaking. And these are some of the more details in terms of how we conduct this Q learning. Because of this very unique domain knowledge, we were able to say that you can train such a nested RL problem, even though it's a multi-agent setting, it can be executed without communication in a sequential manner, right? So again, we are engineers, so we want to also make it not only sound on paper, but also sound in the reality. So this is actually open source deep reinforcement learning based relay training, which connect with a lot of existing commercial grade power system software simulators. And you're more than welcome to actually take it and then try to play with it. The simulation results suggest that this kind of multi-agent RL based relay setting gave us some edges in all of the 3 accounts. That is accuracy, robustness, and response speed. For the traditional relays, even if you push the solar or distributed energy resources to a reasonable level of penetration, you're going to have a major amount of malfunctioning. Whereas in this newly set multi-agent reinforcement learning, things are at least 2 orders of magnitude better. And this is also on the robustness. That is to say, even if you don't know exactly the line parameters and the load profiles, things actually are still working reasonably well under this new paradigm. And this is also the response speed. You want to, whenever such a fault happens, you want to clear the fault within certain time. You don't want to wait for too long. And it shows a very comparable performance with even the traditional relays. So I guess I'll walk you through 2 specific examples of what I call domain-tailored AI. In particular, one is on the bulk transmission level grid. It tries to utilize robust principal component analysis-based streaming algorithm to localize forced oscillations due to some massive renewables. The second example is about developing a nested multi-agent reinforcement learning-based adaptive detection so that when you have lots of solar in the distribution grid, your protection device still work well, perhaps even work better, even than today's low solar situation. During the, this is a kind of a long journey, and I think we're just at the beginning of this journey, but we're already thinking, there are some, quite interesting challenges. For example, a lot of this work is really at the intersection between traditional power systems and the data sciences. So how does one bridge this knowledge gap or leverage each other? And as we are moving along the ecosystems, how do we translate all this great laboratory university research into some quantifiable, tangible, value-added services to the industry, so that as a sector, the energy industry is moving towards a massive digitization. I think these are really interesting challenges, and I personally don't have a good answer yet. I don't attempt to have an answer, but that's exactly what triggered us to think about perhaps one should start to focus more and more on this initiative of tackling the energy digitization. And I'm pleased to report that with the leadership from the Energy Institute, from Stratus and many others colleagues in the Energy Institute, this is sort of have already begun to shape up. We are kind of thinking about three key pillars. One is education. We need to educate a new cohort of students who are kind of I would call it bilingual, right? You have to be good in both energy as well as data sciences. On that front, we've already making some preliminary progress with a strong partnership with the Institute for Data Sciences. And I think there's also a lot of research opportunities. In fact, we were planning to have a on-campus April 24th workshop between the two institutes, the Energy and Data Science Institutes. Unfortunately, again, because of COVID, it has to be postponed, but it already gave us some initial momentum of bringing together on-campus experts at the intersection of energy science, technologies, and data sciences and policies. And then to address the challenge of how do you translate this to tangible industry benefits, we are also thinking about an industry affiliate program such that we can attract, industry members from across the energy and data domains to come in and then, work with us to define tangible benefits for their daily practices. And I think COVID is just another great example of making data-driven, science-based policy making moving forward. And I'm also pleased to report some preliminary examples at this intersection. I don't mean to be just blowing my own horn, but this just happened to be two specific grants that we got recently on this very subject of intersecting between energy and data. You don't have to pay attention to me. I just want to say for those who are researchers, the opportunities are out there for you to grab. So we look forward to your participation. So let me just conclude that I think there is a tremendous challenge as a society post-COVID-19. And one of them will be, how do we make the energy infrastructure resiliency and shovel-ready for this new normal? And in this new normal, there are tremendous opportunities at the intersection of energy and digitization. It is through carefully crafted, domain-tailored AI research, a unique educational opportunity to bring into the next generation of student leaders, and partnering with industry. So with that, I really would like to thank you for your attention, and we really look forward to your participation and your contribution to this journey. Thank you.
Les, thank you so much. It was a wonderful webinar, very, very informative, and definitely you're working in so many different areas, and I'm also pleased to working with you on the educational aspect. For now, we have a question from Professor Enzetti. So, Professor Enzetti, would you like to go ahead and pose the question?
I sent that in the chat channel. So I think I'm intrigued by the example of the PMU data of a generator oscillating in small oscillations in Alberta, causing a major oscillations elsewhere. So you use the algorithms of matrix, the data from the PMU, and then we're able to localize where the problem was originating. Can such an analysis be used in a certain equipment, like a large generator within an equipment? If we had a lot of measurements, can we say, okay, this was the culprit which blew up something else within that equipment?
So I guess, Prasad, thank you for your question. I guess your suggestion is about, so let me try to understand your question a little bit better. are you suggesting that it sometimes is also hard to figure out where the equipment failure happens within the equipment?
Yeah, that could be the case in a complex equipment, which has.
Yeah. So then the second question would be: do we have kind of a lot of such densely, placed measurements in this context of, say, a motor or some other equipment?
Yeah, that is the. It may not be there, but if one were to put it, one were to have a lot of places where one can measure and then collect the data, will that increase my condition monitoring capability?
Yes, the answer would be yes. In fact, I was talking to some Mitsubishi people, and they were exactly interested in what exactly can this AI advanced in motor diagnosis and design. And
not necessarily a motor. It could be an industrial plant, power plant, like an industrial manufacturing facility where there are a lot of different things. And then the outage is such a failure. I'm talking from the electrical point of view. So there could be a mechanical vibration of some bearing being not good.
Right.
And that is going to exaggerate everything else. It's something else which is more expensive in terms of outage. So.
Yes, I think so. As long as we have some measurements, and well, I was talking to one of the major natural gas pipeline providers, and they were thinking along that line. Yes.
Because the model you presented did not really require a understanding of the physical system. It was just purely the data.
Mostly data-driven.
Purely data-driven.
Yes. Levis Stratos, I just want to thank you for your presentation and the link to the resilience of network systems and the power system is an example of this. I wanted to ask you what is your vision of, so most of the analysis you performed was really like sort of given something like, to try to analyze the sensitivity, let's say, or the vulnerability from a resilience point of view of a network. But so how can we use now the information? Can you touch upon the important issue of how can we use the information upon depicting a critical part of the network now so as to improve the network, right? Because that will be like resilience type of improvement as opposed to only analyzing the resilience of
Yes.
Give us your thoughts on the design aspects or redesign, redeployment of resources and things like that.
Thank you, Stratus. And that's a very good question. So it's really about the next step, which is how do we actually strengthen or identify the weakness and strengthen the weakness spot. We have done some work actually along this line of thought of answering the most critical sensors in this network situation. That is to say, if I have lots of sensors, if I cover every single place, maybe not all the sensors are of the equal values. And we can identify where do you prioritize the location of the sensors. Now, the dual of that would be to design where or to prioritize where is the most critical controllers of a network control system. And one can also think of concrete examples of prioritizing this controller design, for example, in a very networked process systems, where is the weakest spot, and I can basically strengthen the loose end, essentially saying that that is where I should be paying attention to in terms of strengthening the controller. On the network itself, it's actually there's a large body of literature on network science on identifying the weak links, and there are a lot of physicists working on those kind of problems. We are making some headways direction toward that, but I think still an ongoing challenge is that by and large, this network science-based approach is taking a kind of a graph-based approach assuming that they are homogeneous, a uniform kind of internal nodal level dynamics. But in a lot of the real world industrial and infrastructure examples, not every single node is the same. In other words, the internal dynamics within each node is actually different, right? If you think about a power plant versus a wind farm with a solar panel versus a city of college station, they're all different kind of internal dynamics. I think it's still very early stage, even for the network science people, to make some headways of analyzing such heterogeneous network dynamics and figuring out the weakness. I'm aware of some of these people, but we're pushing that boundary as we speak. Yeah. So.
Thank you.
We have one more question from Yu Chao, a PhD student from TAMU Education College. Would you like to go ahead?
Yes. Hi, Dr. Scheller. As you may know, I'm a PhD student from Education College, and you just mentioned that possible interdisciplinary collaborations, probably with educational leaderships. As you are speaking from energy institution, you're setting a role model of those collaborations. So would you possibly elaborate that collaboration a little bit further with areas such as education? Thank you.
Thank you for your question. I think this is an important one, and our host today, Valentini, is actually one of the champions of doing that. So I probably can only cover a piece of that, and Valentini, please feel free to chime in. I think it's really, I think this boundary of different domains, how to do this education is really a big challenge, because you want to increase the breadth, but in the same time you don't want to sacrifice the depth. And but then you have a limited number of hours for each student, and a lot of these hours are now eaten by the social networking, and so your useful hour is actually reducing. So what we have been doing on a smaller scale is trying to say, okay, let's find some common core, right? So for example, in the energy, master science program, the common core would be a basic knowledge of energy processing, and then the basic knowledge of data sciences. And we ask experts to teach those in as a broad, as abstract manner as possible. And then we allow the students to kind of tailor and choose whichever specialties they want to participate later on. So really is to, I guess the goal is to say, I mean, my answer to you would be to separate or to identify what is common core and what is specialty. Yeah. And Valentini, would you like to maybe say a few things about?
No, at least in our program, the breadth is what is important. And if you want to have an interdisciplinary education, you really need to be aware of all the different issues and matters. Now with energy digitization, joining the Master of Science in Energy definitely broaden up a lot of our audience and a lot of opportunities for applicants. I will be happy anyway to discuss further that with you, as I know probably you're interested on methods and other aspects on the future education, if you like. So I will be happy to take that offline and discuss further.
Thank you.
We have a question from William Burns. Would you like to go ahead? No, thank you. No, sorry, it was a message to thank you, Le. And the last question here is from Paiman Dahanian. Apologies for the spelling of your name. He hasn't got access to a microphone. So the question is, while PMUs can provide useful information of grid scale wide area awareness of the grid, the centralized monitoring and control paradigms are still vulnerable to cyber attacks and communication delays on PMU data while they transfer the control centers. Do you see a potential for a distributed capturing and harnessing of PMU data with lower requirements to long distance transfer of measurements?
What's the last sentence?
Do you see a potential for a distributed capturing and harnessing of PMU data with lower requirements to long distance transfer of measurements?
I see. So basically the question is about, can we actually just manage some of those data locally without changing them? I mean, sending them all along to the control center. I think the answer is yes. In fact, there were some technology, invention provisions about how do you actually modulate and cut majority of these measurements in normal times, keep them all local, and then only send the critical pieces to the control center once you have figured out some trigger of those events. So yes, very much along that line of thought. And with all this proliferation of edge computing and edge decision making, this is likely going to be the trend. But I think for a critical infrastructure, another point is that when it comes to forensics, to post-event analysis, it's still important to draw correlations from each other. So there is still, I think, a role of cross-comparing across different domains at different times in one supercomputing. That may be for post-event, not for online purposes. Yeah.
Yeah, I think that were the questions. I don't know if somebody else has a question just to chip in. So I would like to thank you for today's webinar. Your presentation will be available, and we'll send it to the attendees, and thank you for sharing that. Regarding future events, information will be on the flyer, and also follow our website, Texas A&M Energy Institute under events, where a lot of more